Oh. Any other questions on the syllabus before we go ahead and get started on some stuff? All right. So let's talk a little bit about what the video covered. I'm not going to obviously go back through the details. I don't expect that you're going to reproduce that at any given time, that argument that was on the video. One of the reasons, was that?
I took extensive notes.
Well, good. I'm glad you took notes. That's good because the whole point of that was the idea of somebody has stuck a piece of metal in this outlet, or a plug-in has broken off in the outlet, but there's metal sticking out of that outlet.
Maybe you should touch it.
That's probably not a good idea. I think I want to stay away from that and tell somebody that that's in there. Anyway, I got distracted. All right. But the point of going through that particular idea was splitting up the one random variable into the two pieces and looking at the degrees of freedom for the pieces that we had, right? So you had the one distribution that you knew for a fact the underlying distribution was normal, and you squared it, right? You had the x minus the mean, the population mean, over the standard deviation. So doing that z-score, right? And squaring it. So the x minus mu over sigma was the standard normal. So again, that was a review, because we're going to be doing z-scores, right? That is something that we're definitely going to do this semester, is computing those z-scores to get things, right? And using the normal distribution table, that kind of stuff. So that was reviewing that when you do that shifting and adjusting by the variance, you get the standard normal. You square the standard normal, you get chi-squared, right? With 1 degree of freedom. And you add chi-squareds, and they're independent, you just add it in the degrees of freedom, right? So that was how that, in that video, that was how that left-hand side of the equation came up, right? It had the sum of all of those things out of the sample, subtract the population mean, divide by the population standard deviation, you got the chi-squared of n, right? So if I just write that down, real quick, just kind of review through it. We had the sum from the I equals 1 to n of the x sub I minus mu over sigma squared. That was chi-squared of n. So that was one of the reasons why I wanted to go through that particular thing, was just to review that stuff, right? And another reason why I wanted to go through the... Yes, sorry.
I wrote down chi-squared. Maybe that's wrong.
No, that's just the s squared. I'm not to that point yet.
Oh.
I'm in midway in the proof part, rather than the theorem part. So you're looking at.
Yeah, I see.
Yeah. Yep. Okay. So anyway, this turns out that you can break up into two pieces, right? It had the piece that was. There was an n minus 1 in front, and right this way, over sigma squared, and then it was a 1 over n minus 1. Oops. Trying to remember what it looked like. That was one piece? Oh, yeah. That's because this is here. Sorry. Yep. Sorry, that was here. I put it in 2 different spots. Thank you. No, why is it running low? It was plugged in all last period. You might want to plug in your PC. What if I wanted to run out of battery? Did you ever think about that? Did you ever think about that, Microsoft? That's right. Oh, good grief. I'm really hesitant to put this in this over here. I really don't want to touch it.
Touch it.
No. All right, did it actually?
For science.
Oh, that's why it's not working. Probably because it's shorted out because it's got a metal plug stuck in it.
Were you in this classroom last period?
No, Dr. Stickles was, but she doesn't use the plugs.
There's one over there.
Yeah, I just want to triple, right? Because I am kind of clumsy.
We'll just make sure it's flat on the ground.
That doesn't matter. Have you seen me walk? That doesn't matter.
At that point.
All right. It's plugged in. Cool. All right. So we broke it into two pieces on there. This was one of the pieces. The other one was just a single, just a single piece, right? It was x bar minus mu over sigma squared. Oh, yeah, it did. You're right. You better have. That's what I get for going by memory. It's not very good. All right, anyway. So why did I put this part in here? Well, this part here is reviewing central limit theorem idea, right? If each of your x's are normal, what do you know about the distribution of the x bar? It's also normal, right? What's the mean? Same as the population mean, right? For the underlying population. What does it do to the variance? Divides it by n. So your standard deviation gets divided by the square root of n, right? Again, this was all stuff from last semester, right? So one of the reasons why, besides the point, what did I just tell you?
Why don't you walk to your left instead of your left?
Stop trying to be helpful. It's not going to help. It doesn't matter. I'll just trip over something over there. Plus, I might get shocked by the thing sticking out of the pole.
That's if you touch it.
You don't know.
Electricity's just going to surge out of it.
Absolutely.
You got me.
All right.
5 minutes from now, it's just going to explode.
All right. So this was stuff that we talked about last semester, right? There was central limit theorem. We talked about what happens when you take variables over and over and over, independent and identically distributed variables, or thinking about it from a sample perspective. When you sample over and over and over again for the same population, what happens to the distribution for the sample mean? Right? For normal, it's automatically normal. If it's not normal, it becomes approximately normal if your n is big enough. Right? That was stuff that we talked about last semester. So there's another reason why I wanted to go through this, but in particular, since this is normal, we standardized it and squared it. So this was chi-squared of 1, right? So this piece is the chi-squared of 1 piece. But again, that goes along with the same idea of why that one was chi-squared of n, correct? You're taking the distribution, you're taking a normal distribution, you're subtracting off its mean and standardizing it, right? Standardizing the variance, making it standard normal, and squaring it. So that makes it chi-squared. This idea, I did that on purpose. This idea is to add up those independent chi-squares and make it still chi-squared. Right? So where did this part fill in? Well, we used basically what did we do? We took this, changed it into a moment generating function. We did the same as this moment generating function. And then the idea behind the review was you have a sum of independent random variables. That was the thing we can't prove yet till later in the semester, that the x bar and the s squared are independent, which is weird if you think about it. At least I think it's weird. Why do I think it's weird? This is s squared, which is defined in terms of x bar, but yet as random variables are independent of each other. Meaning that when you do sampling, what mean you get doesn't affect what a variance you get. If you do it over and over and over and over and over again. The distributions are independent of each other. Obviously, when you do this variance, you use the same mean that you get. But from a distribution standpoint, they don't depend on each other. From a probabilistic standpoint, and from a distribution standpoint, it's weird. I agree. I see X bar in the computation of S squared, but from a probabilistic standpoint, they're independent. Meaning the probability that you get a particular mean and the probability that you get a particular variance don't matter. They don't have any effect on each other. Okay? So that's just that idea of review of independence. But the idea was then, when you do moment generating functions of sums, they turn into products of moment generating functions. The reason, again, because of that, is because how is, from a definition standpoint, how is your moment generating function defined? Yeah, it's the expected value of that e to the tx, right? So if you've got a sum up here in your exponent, how do I rewrite it? If you have a sum in the exponent, how can you rewrite it? It's a product, right? So if you've got, in general, if you've got some moment generating, write it this way. If I do expected value of e to the tx plus y, that's e to the tx times e to the ty, right? We agree? Okay. So this was one piece that I wanted you to remember from moment generating function ideas. This is for later in the semester. You need this kind of stuff to be able to prove that x bar and s squared are independent of each other. You need to go back to moment generating function ideas. But the fact that these are independent now allows you to do what with the expected value over the product? You can separate them, right? So this is the expected value of e to the tx and e to the expected value of e to the ty. If x and y are independent. Okay? So that was another thing that I wanted you to get out of that. This is the main, besides the fact that I think it was instructive to go through the idea of the proof and see where that n-1 piece comes out of, figure sample variance. There's a lot of review from what we did last semester in this one thing, right? Lots and lots of review out of here. So then at this point, we just, when you broke it up in the video, we broke it up, we just moved the one piece over to the other side and recognized that it was a chi-squared. But again, that was another thing that we could review. We said, once you know the moment generating function, you know the distribution. We used that fact that said it was chi-squared of n-1. So one other thing that was kind of buried that is an important idea was that idea when you sum up the deviations. If you sum up each x of I minus x bar for a sample, you get 0. The sum of all the deviations is always 0, no matter what. That was also in there. That's just a nice fact to remember generally, that always has to happen. It's nice. I mean, of course, you do so many things on the computer anymore, it's not really relevant, but it's nice as a check to make sure you've done things correctly. Sum up your deviations to see if you get 0. If you're actually trying to compute the variance, for example. Because it should always get 0, or if you've got some rounding, it might be 0.0001 or something goofy because it was rounding error. But it's a nice check as far as those things go. Yeah, Grace?
You referred to things you do on the computer for the time class. Are we fixing graph?
It might be helpful from time to time if we're going to use something on Excel, and I will do my best to remember to tell you when to do that. Only because there will be some specific types of things we'll want to compute. I mean, I might show you a command from time to time on Excel, but that's just something you could write down and use. It's not anything that's a big deal. But there will be some testing of things that we'll do that we'll want to use Excel and not do it by hand. But any stretch of the imagination, we'll not do it by hand. Okay. I will do my best to try to remember to tell you that when that happens. But I'll also plan on posting videos of how to do that too. So if you don't have your computer that day, you'll at least have a video to go back to, a short video as an example for how to do it. That's also my plan for that. All right. Anyway, so back up to this piece here, just to talk about this just a little bit more. So we typically refer to, without this n minus 1 over sigma squared part, we refer to this part right here, you have usually as our sample variance versus our population variance, right? The s squared, 1 over n minus 1, sum I equals 1 to n of x sub I minus x bar squared. That's our sample variance, is usually what we call this. There's a couple of reasons why we use the n minus 1 piece out of this. One is because it made the stuff work above, right? It was the fill-in piece that we had to prove, right? Another part is because it was the piece that came up with how many degrees of freedom we needed, right? We had the degrees, the chi-squared of n, the chi-squared of 1. It was the fill-in piece that we needed. It needed to be chi-squared of n minus 1, right? So that's, from a theoretical standpoint, that's where the n minus 1 piece comes from. Okay? It also makes things work as far as actually trying to estimate what the variance is for the population. Okay? We're going to talk about the idea of estimators in the next chapter, but the whole point, if you have an estimator, if you're calculating, if you're using the sample to calculate a guess, an estimate for what the population parameter is, you would like its expected value to be if you do this over and over and over and over again, you would like that expected value to be the same as what the parameter should be. What I mean is, think about for your means. If I'm trying to estimate a population mean, I'm going to use the sample mean to estimate it, right? What I mean is that we would want the expected value of the sample means to be the population mean, right? That's generally what we would want, isn't it? I don't want to say, oh, I'm going to calculate this statistic, but it doesn't really give me what I want, right? I'm trying to get a handle on this. I want this to be true. If I run sample after sample after sample after sample, I should get this expected value. I shouldn't be getting that population. Okay? What we refer to this is that if this is true, we say that x bar is an unbiased estimator for the mean. Oops, that's a mu. And unbiased is a good quality for an estimator to have. Now, if you know what the bias is to start with, you can adjust for it. But in general, unbiasedness is what you want, is a quality that you want. Okay? Because you want to know that if you run samples over and over and over and over again, it's giving you a good handle on what the population parameter should be. Okay? So, going back to the sample variance over a population variance idea. If you do the expected value of s squared, well, our s squared is defined as this 1 over n minus 1 sum I equals 1 to n of x sub I minus x bar squared. Right? What by heart? I'm sorry.
S squared.
You should know what s squared is, yeah. But it shouldn't be a surprise because it looks like a lot what sigma squared is. If you were doing expected value for, because this is your. I'll talk about it in a second. In a minute. Okay. But yes, you'll need to know that. All right. Anyway, I want to get this in terms of how I can calculate this expected value. Well, one thing I know that I can do is I could pull this thing out in front, right? So I can pull the 1 over n minus 1 out in front. I'm also going to add in the population variance on the outside and then put 1 over the population variance on the inside. But to save space, I'm going to do 2 steps at once and then stick it inside the squared. It's basically that middle piece that we had in the proof. Why did I do that? In particular, why did I put the variance in there? Why did I do this?
Standardized.
Yeah, standardized it, right? Okay, so this is going to be chi squared of how many degrees of freedom?
1.
What was it in the previous? It was n minus 1, right? So this is chi squared of n minus, this piece right here is chi squared of n minus 1, right? It's just the inside of the chi squared thing, right? What is the expected value of a chi squared distribution? That's exponential. It's what?
It's somewhere still.
It involves the R, I agree. It's not R theta. Where's theta coming from? There's no theta.
Oh wait, just R.
It's just R, right? No, you didn't. You said all sorts of weird stuff. Yeah, the expected value is just the degrees of freedom. The expected value of chi squared of R distribution is just R. It's just the degrees of freedom. Okay? So what do we get here then? We just get sigma squared. Right? The n minus 1's cancel. So from a practical standpoint, here's what I mean by practical standpoint. The whole point of doing statistics is trying to estimate population characteristics from a sample. The whole point. I mean, there's lots of different ways you could possibly do that. But the whole point of doing statistics is to estimate the bigger picture from a snapshot or a piece, right? Okay? Trying to know what the jigsaw puzzle is from picking out one piece, essentially. Okay? What does the jigsaw puzzle look like if I pull out one piece? Now, I probably get a piece of blue sky and not know anything about it. Let's see what I would do in my life pulling up the jigsaw puzzle. But that's the idea behind statistics. Okay? So if I'm calculating a variance from a sample, the reason why I would be doing that is because I'm trying to estimate the population variance. There's no other reason to do it. Okay? Now I might do other things with it to do some inference, but the whole point of calculating the sample standard deviation, or the sample variance, I mean, is to estimate the population's variance. There's no other reason to do it. Okay? Unless you really enjoy arithmetic. That would be all it is. Okay? Me? No, I hate arithmetic. Okay? So, I'm trying to estimate the population's variance. If I do this if I think about doing it over and over and over and over again for various samples, I would want the expectation that those samples all those sample variances have an average of being the population's variance. I would want, when I take the expected value, I would want to get the population variance out of it, right? If I have n instead of n minus 1 to calculate my sample variance, I would have a biased estimate. The n-1 piece in there is what's giving us an unbiased estimate, which is, again, a quality of an estimator that we would like to have. That's the point, well, that's the practical point of having an n-1 in there instead of an n. Does that make sense? All right, cool. All right, so let's see if we can actually do a practical problem that involves this. By the way, the other two pieces that I mentioned at the end of the video, the reason why they were very, very short is we'll do more of that later when we get to it. But I wanted to introduce it then because they do pop up. So again, it was one of those things I just wanted to get in front of your eyeballs and in your mind because it's stuff that we're going to do later. The t-distribution pops up when we do small samples rather than large samples. Small samples and we don't know that it's normal, but we still want to try to do some sort of an inference from it. The F distribution pops up when we start comparing variances. Again, you should be able to look at the form of those distributions and understand why it's doing similar things. Notice the t distribution was normal divided by chi-squared. That's square root of the chi-squared, right? That looks like what you do when you do z-scores, right? It looks the same, right? Because on top you have x minus the mean, and on the bottom you have the sigma. That's your z-score, right? And then you've got that dividing out by degrees of freedom or dividing out by how many things are in your sample. It looks like doing z-scores. It's just for small samples. The reason why you have to do that for small samples is because the variance is bigger. And that was what those pictures in the video was meant to show. I don't know if it was helpful or not, but that was what it was meant for. Yeah, Chris?
I'm hearing questions about it. For the T and F distributions, is it like universally T and F? Like if you went up to a random mathematician and it's like, yo, the T distribution.
Mm-hmm. Yep.
So it's not just like a random.
No, it's universal. The T comes from the fact that it's the student's T distribution. The person was coming up with ways to check beer quality of all things. It worked for a beer manufacturer. It was, I believe it was Guinness, yeah. It worked for a beer manufacturer, was doing beer quality testing, and wrote about what kind of statistics he was doing to do the testing of the beer quality, and wanted to be taken seriously rather than saying, hey, this is coming from Guinness. So he just wrote under the pseudonym of student. And it was the T distribution, so it's student's T distribution. That's where it comes from. So yeah, if you talk about these T distribution, people are going to know what you're talking about. Yeah. And then the F distribution, again, you can see why you might be talking about testing. One of the big things that you need to test for in some of the hypothesis testing is whether or not the population variances are the same. Or if you do a ratio, whether or not the ratio is 1. And so you see those ratio of chi-squared distributions pops up in that F distribution. It's the only reason why I was mentioning it in that video. It popped up in section 5.5. We're not going to do much with it yet. We will. As with getting it in front of your eyeballs. Okay. All right. So let's see if we can do an example here. So let's look at 5.5-7. And I want to look at part B. So I'm not going to go through all the setup of this, but X is normal, mean 8.78, variance of 0.16, and it wants you to find A and B so that the probability that S squared is less than or between A and B is 0.9. All right, so there's actually quite a bit of ways to do that. You can move the A's and B's, but we're going to use the chart for the chi-squared, so hopefully it'll pop up for what the A and the B need to be. But we know that s squared has a certain distribution, but we have to do some adjustment with the constant, right? S squared itself is not chi-squared of n minus 1. It's n minus 1 times s squared over sigma squared, right? Right? It's when we have the s squared piece, that itself isn't quite chi-squared of n minus 1. We have to multiply it by n minus 1 and divide it by sigma squared. That was the theorem, correct? Okay. So we know that n minus 1, I guess I need to tell you what the sample size is because I told you in the problem. N minus 1 s squared over sigma squared is chi-squared of n minus 1. They tell you in the problem that n is 9. That was what I get for not writing down the whole problem. I forgot a piece of it. You need to know that piece. Okay. So, let's see. I think I have the chi-squared table still stored in here. There it is. All right. So, if n is 9, how many degrees of freedom should I be interested in?
8.
8, right? Okay. So remember our chi-squared table? Okay. So the subscript at the bottom is giving you the probability of the tail, right? And remember the top is the probability, or the right tail, I should say, and the probability of the top is the left tail. Okay. So we're looking for a region that gives us 0.9. Well, they probably want you to do the 0.95 and the 0.05 to get that. I think it's the only is that the only combination that's going to give me 0.9 out of this? I think it's the only possible combination we can do in the table. That'll give me 0.9, right? Because they want the two numbers where the probability is 0.9 to be in between. If I subtract probabilities, I think the only one that's going to work is 0.95 and 0.05. From the table, it's the only way I could do it, right? I could do 0.97 and 0.07. I don't see it in the table. If I had Excel, I could do it, and I will show you how to do these things in Excel to find these values, and you won't have to ever go back to the table again. Okay. But that's not today. All right. So here's my 0.95 column. Here's my 0.05 column. I need to get to 8 degrees of freedom. So here was the 0.95, here's the 0.05, right? We agree? If my value for my variable is in between those two values, then I have a probability, the probability that a chi-squared, well, I'm in the wrong row. Try that again. I thought I was in row 8. This one and this one, sorry. All right. So we went to row 8 because there's 8 degrees of freedom, n minus 1, right? I want the probability of being in between two numbers to be 0.9. There's only that set of two numbers that gives me 0.9 to be in between, right? Everybody see what I'm saying about that? Yes.
So because the problem's asking for two numbers that are in between, you can't just use the 0.9?
Correct, because it's asking for two numbers that it's in between, right? Yeah, if it had just said one number to be less than 0.9, then yeah, I would go here. Yeah, that's why. But I'm trying to figure out the combination that gives me 0.9 for being able to subtract. It's just that's the way the problem was set up. Like I said, if we have Excel, then it really doesn't matter. I could just pick two numbers that have a difference of 0.9 and use whatever I want. Okay. All right. So, hey. Anyway, these aren't A and B, by the way. They're close. Okay? The reason why they're not A and B, remember those numbers, by the way, so you can tell me what they are in a second when I forget. Okay? Because we all know I will forget. Where is the... what's it? Up? Oh, there it is. Thanks. Okay. All right. So, what was the first number? 733. That was a 5. And the second number was? Okay, cool. All right. Now, this isn't quite s squared. What has a distribution of chi-squared of 8? It's not s squared. What has a distribution of chi-squared of 8? Yeah, the n minus 1 s squared over sigma squared, right? So this is going to be 8s squared over 0.16. Because 8 is n minus 1, and 0.16 is sigma squared. So then you would just need to solve for s squared. So we just picked the two numbers off the table, the 0.95 and the 0.05, because that was the way the problem was set up. They wanted two numbers, right, to be in between. I just had to adjust my s squared to be able to get it off the chi-squared table. All right, I know. Sorry about being late. I really didn't mean to the first day of class, and I know some of you have to run over to history, so I apologize.